Hi everyone. In this lecture, I will provide brief overview of brain-computer interfaces. This presentation is part of the Human-Computer Interaction course CMPE496 offered in Boğaziçi University in the spring 2025. The images presented in this presentation are from various sources, including technical papers and magazines. I'd like to acknowledge their contributions and thank them for supporting open source science. To start, here are some key references and recommendations and recommended readings on BCIs, particularly ones on ethical and futuristic implications on humans are worth reading and contemplating. As you can see from the charts, research in BCI has been growing significantly over the past decade, with the United States, China, and Germany leading in the publications. This field is rapidly expanding. It's not just academic papers. The number of patents related to BCIs has also seen a dramatic increase in the last decade or so, indicating growing commercial interest and innovation in this area. This data is captured from PubMed and PatSnap publications between 1991 and 2021. So, where does BCI fit in the big picture? This representation presents an evolution from general man-machine communication and traditional human-computer interaction, focusing specifically on using brain signals for control. Let us contrast BCI with the traditional human-computer interfaces. While the human-computer interface relies on physical inputs like keyboards or touch, BCI aims to interpret brain signals directly, bypassing physical actions. It considers human perception, interpersonal factors, and physiology interacting with technical systems via various sensors and stimuli. Traditional human-computer interaction primarily uses muscular activity. Giving you an example, think about common devices like mouse, keyboard, joystick, or steering wheel. They all require physical movements. In contrast, the brain-computer interface, or BCI, allows direct control of devices using brain activity alone, without any muscle movement. Let us consider the following generic workflow diagram. This diagram shows a typical BCI system where brain signals are acquired, processed, and translated into commands to control a device like a wheelchair or a neuroprosthesis. Feedback is often provided to the user visually, auditorily, or through touch, through our haptic system. Brain signals can vary from electroencephalography or electrocardiogram to fMRI and other brain imaging techniques. These techniques have pros and cons which will be discussed later. Before diving deeper, let us consider two fundamental and to me very relevant questions for the motivation of these systems. The first question is how significant is the BCI in our world and commercially? The second question, how well do we actually understand the brain's functions to be able to design such interfaces? Historically, the concept of brain-computer interface might have been equated simply with a graphical user interface. The generations of technology development might have portrayed a simplified interpretation of BCIs. Now, in today's world, BCI is understood as a much richer, multimodal interaction environment, incorporating not just brain signals, but potentially other physiological data like heart rate or skin conductivity, in addition to brain's responses. So, why is human-computer interface, and by extension BCI, important? In my opinion, it relates to the concept of human alignment in an AI broadly. Intelligence can be defined as selecting actions based on perception to achieve objectives. One might remember that the standard AI model focuses on optimizing pre-specified goals, However, if these goals are misspecified, especially with the super intelligent AI, it could lead to harmful outcomes. On the other hand, a better model involves a human-machine partnership, where AI will act to fulfill human objectives, not just its own fixed ones. Assistant games, for instance, offer a framework where machines learn how human preferences change, through interaction. Building AI with uncertainty about human values would be the key for safety, prompting it to seek input and be more controllable, which might have implications in the design for future BCI systems. The ultimate goal is to shift from a self-contained view of AI intelligence to a human-aligned approach, ensuring AI to be provably beneficial. So I would like to draw your attention to the disentanglement problem. Human intelligence integrates objectives, actions, and embodiment, linked by causal relationships, mostly due to physical world and its inner working principles. On the other hand, these are the fundamental verticals and can be completely disentangled. This created a whole series of issues and questions about the development and management of intelligence. In fact, if we assume the real source of objectives to be humans, then in human-machine system, the interface acts as a potential noisy channel, translating human objectives to the machine objectives. That's the ideal case. However, this imperfect translation could potentially lead to uncontrollable machines or agents that can behave unpredictably. Therefore, the interface design is quite crucial for accurate translation and eventually aligned AI. I'd like to give you a quick overview of the brain, which would be quite useful for the rest of our presentation. Here, I'm showing you different dissected areas of the brain, specifically specialized for performing different functions. Different lobes handle specific functions here. Frontal for executive tasks, motor for movement, somatosensory for touch, parietal for spatial awareness, occipital for vision, temporal for auditory processing and memory, and auditory cortex specifically for sound. The concept of using brain signals for man-computer dialogue dates back to 1973s. Early goals focused on providing communication for severely disabled individuals, viewing the machine as a prosthetic extension of the brain. As indicated here, the premise is that computers could become seamless extensions of our cognitive processes, not just tools we operate externally. A broader definition sees BCI technology as systems converting central nervous system activity into an artificial output to interact with the environment. Historically, there are two major challenges for brain-computer interfaces to be prolific. And these challenges have been low information transfer rates, and the need for long training times. I'll try to address what we mean by these criteria and how can the novel technology addresses these issues. Brain data can be extracted using various methods. These methods include functional MRI, electroencephalography, magnetoencephalography, and functional NIRS. Each has their own pros and cons, and the technology behind these techniques also different, but they could be attractive for a given application at hand. Brain-computer interfaces have boundless potential applications, aiding communication for paralyzed patients, health monitoring and diagnosis, enhancing education, augmenting cognition for faster responses, and even in entertainment and security domains like gaming or advanced lie detection mechanisms. One of the interesting and recent applications is related to exoskeleton in an attempt to help build superhuman power engagements. BCIs have captured the public imagination, appearing in sci-fi. Commercial systems like Emotive exist, and we see a lot of depictions of similar technology in sci-fi movies. One most popular application that seems to appear in movies and theaters is reading one's mind. The concept of brain fingerprinting claims to detect crime-related memories by analyzing brain waves. Brain fingerprinting, developed by Larry Farwell, uses electroencephalography to determine if specific information is stored in memory. While used in some cases, there are concerns about its reliability due to factors like false memories or suggestibility. The core idea is that crime-related information leaves a permanent brain record. Hence, through brain imaging techniques, this record can be stimulated and be read from the elicited signals for later processing and detection. Brain-computer interfaces can be categorized based on how the brain activity is generated into three distinct categories. First one is active brain-computer interfaces. These uses consciously controlled brain activity. The second one is reactive BCI. It uses brain activity reacting to external stimulation. And passive BCI uses spontaneous brain activity to infer cognitive states like workload or attention without conscious control. Alternatively, we could classify BCIs based on the signal types generated by the neurons. Common brain signals used in BCIs include visually evoked potentials like SSBPs, slow cortical potentials, and other evoked potentials like ERPs, including P300, and sensorimotor rhythms. I'll be mostly focusing on ERPs and visually evoked potentials throughout the presentation. But this taxonomy here is quite important to provide you a spectrum of signals that can be elicited through different brain mechanisms. Signal acquisition can be invasive, involving electrodes placed inside the brain or on its surface, that we call cortex, and through technology called electrocorticography. ECOG, in short. This is common in animal research, such as mouse, mice, macaque subjects, and sometimes in human patients undergoing surgery. Implants can also be used for neural stimulation, like in Parkinson's treatment. ECOG recordings here show changes during movements, such as hand movement or imagined movement. The signal's frequency content seems to change as we engage with the motor activities. Through a simple frequency transformation reveals the decreased power in low frequencies and increased power in high frequencies, as shown in the figure located in the middle. Imagined movements also demonstrate similar activations, but this time weaker signals are produced than actual ones as shown on to the right. I would recommend to take a look at a video for the full coverage of this material. We will be focusing primarily on electroencephalography due to its practicality and widespread use in current BCIs. In EEG, we measure voltage changes at the scalp due to neural activity. This provides good temporal resolution, but a bit of a poor spatial resolution. Through EEG, we can actually collect a lot of data through electrical signals. However, the advantage of the EEG is inexpensive and therefore most common in every product you see, under BCI categorization. EEG uses scalp electrodes, typically gel for super conductive environments, often arranged in 10-20 system to measure microvolt level voltage fluctuations from cortical neuron activity. Signals pass through skull and scalp, requiring amplification and facing attenuation. Not only skull and scalp, but there are also membranes that you need to travel through to be able to get the signal out from the brain. Recent advances include active and dry electrodes as well. The acquired signal is pre-processed and further analyzed for future extraction. These features are later classified to take action to control an application, for instance. The final feedback is used to adapt. EEG signals are often analyzed by frequency bands, like delta, theta, alpha, beta, or gamma bands. These bands span specific frequency ranges as shown in this slide on the right. These waves offer a non-invasive look into brain function and cognitive states. In fact, abnormalities in specific EEG wave patterns are associated with various health conditions. For instance, gamma with the schizophrenia and autism, beta with anxiety and Parkinson's disease, alpha with depression or ADHD, theta is also affiliated with ADHD and learning disabilities, delta with brain injury and dementia. This mapping could be used for identification of the treatment needed for patients to regain their cognitive health. I'd like to mention two key EEG responses used in BCIs. One of them is ERD-ERS, event-related desynchronization or event-related synchronization. These are measured changes in power within specific frequency bands, often linked to movement or imagery. When we filter EEG signals, we can obtain event-related oscillations. These oscillations could be synchronized, in which case amplitude increase, the frequency response support decrease, or desynchronized to decrease amplitude and increase the spread of the frequency content. This is like, you can think of it as like deconstructive superposition. This is actually related to mental or motor activities, and these mental and motor activities can control size synchronization mechanisms. The other important response is evoked potentials, EPs. This can be obtained through simple averaging to mitigate background noise or task unrelated noise. Stereotypical responses to specific stimuli, such as P300 signal, can be obtained to compare in the temporal direction. As one of the ERPs, the P300 response is a positive potential occurring about 300 milliseconds after a significant or attended stimulus, like a mental aha moment. Classifiers can detect the presence or absence of P300 component in the EEG signal. As you can see on the bottom right, the green curve is for the P300 component, and non-P300 is depicted as a dotted red line. You can see that the target is present with the green line, whereas it's not present for the dotted red line. EEG data is typically represented as signals across multiple channels over time, often segmented into epochs related to specific events or stimuli. There are many successful applications that use ERPs in controlling external devices. Early successes include P300-based typing systems and classifying EEG during mental tasks to control joysticks or even toy cars. Let me talk about the P300 speller application, which allows users to type by focusing on characters in a flashing matrix. When the desired characters, row and column flashes, the user attention elicits a P300 response, which the system detects. It's relatively easy to use, but can be slow and sensitive to disruptions. An example, P300 deflection in the average EEG signal, which is shown in blue, is shown on the bottom right and superimposed on the control signal, which does not include P300 component, as shown in the same figure. Variations exist, of course, in the original P300-based speller applications, like using faces as stimuli, which can enhance the P300 response and involve other ERPs like negative 170, which is a biomarker for faces in humans. In the past research work, it has been shown that using familiar or even one's own face can further improve the performance of these spellers. Finally, I want to talk about SSVP, steady-state visually evoked potential-based spellers. These spellers use stimuli flickering at different frequencies. In the speller application, each character is paired with or tagged with a specific frequency. When the user stares at the target flickering at a specific frequency, their EEG shows a response at the same frequency in the steady state, which allows the system, in fact, to identify the target. SSV BCIs often offer high accuracy and speed, better information transfer rates, but can cause visual fatigue in the long run. Challenges with EEG BCIs include cumbersome setup, variability in signal quality from day to day, subjects' mental load or being under the influence of various chemical substances, such as coffee or caffeine, low signal noise ratios, requiring sophisticated algorithms to be employed, and limited spatial resolution, which is mostly due to signal attenuation problem. Just to recap, the non-invasive methods like functional MRI, slow, MEG, magnetoencephalography, a bit expensive, and electroencephalography, which is the most common technique despite its limitations. I would like to also consider the MEG option, maybe for a few slides, before I conclude my presentation. MEG measures magnetic fields from neural activity. It offers excellent temporal resolution and also better spatial resolution compared to EEG, because magnetic fields are typically not distorted by the skull. However, it's very expensive and requires a shielded room and big magnet to capture low power magnetic energy, and it requires staying still, during the experiment session. The magnetic field is formed by the created electrical field due to spiking neurons and the exchange of chemical material during the information transfer among neurons. Let us remember the BCI categories again, that we had active BCI, relying on conscious control, reactive BCI, which is created response to an stimuli, an external stimuli, and finally the passive BCI, which is monitoring spontaneous activity. I'd like to now focus on this passive BCI, the third category, which is a brain-computer interface which derives its output from an arbitrary spontaneous brain activity without the purpose of voluntary control. This would enrich our human-computer interaction with implicit information. Passive BCIs monitor cognitive states like workload or attention from spontaneous brain activity without the user actively trying to control anything. Goal is to provide implicit input to an adaptive system. A key application of passive BCIs is monitoring driver drowsiness, detecting changes in neural activity indicating sleepiness could trigger alerts or adjust car systems like temperature or music volume in order to increase driver's alertness. This can be directly applied to driver assistance systems. This slide here illustrates the concept of using brain-computer interfaces for creating the right environment for safer driving. Of course, this requires additional processing units that could, for example, monitor the traffic or the road conditions and could assist the driver with emergency braking or take alternative actions to prevent undesired outcomes. The BCI domain is quite rich nowadays. An emerging trend, for example, in the BCI research is brain-to-brain communications, aiming for direct information transfer between individuals using BCI as the emitter, but also the CBI, computer-brain interface, as the receiver, often involving technologies like TMS, for instance, transcranial magnetic stimulation, for the receiver's side. Here, CBI is the counterpart to BCI, and it is a more challenging area of research, which is supposed to create an incoming visual or data inside the brain's functionally specialized locations to compose perception. This technology still can be considered to be in its infancy and has required a series of revolutionary innovations, including public safety and regulations for widespread use in the future. Despite innovative applications, remarkable progress has been made in the fields of BCI research. The major challenges still remain. On the hardware side, for instance, we need better, less noisy signal acquisition techniques for both invasive and non-invasive methods, including biocompatible implants. On the software side, we need more robust and adaptive signal processing techniques, maybe machine learning algorithms, which are needed to accurately map brain activity to desired outputs. BCIs raise significant ethical questions as well, blurring the lines between humans and machines, privacy and safety concerns with the implants, potential misuse in law and warfare, like brain fingerprinting or brainwashing, and societal impacts regarding augmented capabilities, creating new inequalities in the society in a broader sense. I think I'll stop here for now. I'll be happy to have your questions. Should there be any comment, please feel free to email or drop your comments down below.